Right, we studied the formation of acetal. You know the acetal you produce use alcohol and some of those aldehyde or ketone. Okay? Then some of the compounds have both of them in the same molecule, in the same structure. Okay? So therefore you can produce cyclic hemiacetal. And so that's why the hemiacetal is most is stable, so therefore sometimes you can, if you only produce the hemiacetal, you can use either acid catalyzed or base catalyzed. And here we have two examples of molecule that has the first one we have the aldehyde unit and we have the alcohol unit. Okay? So therefore you can produce the acetal or the hemiacetal. So usually for those kind of molecules, you will produce the hemiacetal is stable than the open chain. And obviously you cannot produce from one molecule produce the acetal because you need two alcohol. So once you produce the hemiacetal, then you can add in another alcohol. But for those kind of cyclic structures, they are already stable in the hemiacetal. So therefore you can isolate. If you want to do acetal, you add in some other alcohol, and that can also happen as we were studying in Chapter-17. So usually, if you want to produce a cyclic structure, the 5-member or the 6-member range is stable. Okay? So just identify. You need this carbonyl carbon in the range. You need this oxygen in the range. Okay? So therefore 1, 2, 3, 4, 5. So these 5 atoms will be in that pentane cyclic structure. And you see this K is about 8. So not than 1. So therefore it favors the product. I will redraw this molecule on top and number those carbon. So you will see which carbon goes what place. This 1, 2, 3, 4. Your carbon 1, 2, 3, 4 right there. The second example, you already have the number. We have to just identify which of those OH you can use to produce the most stable hemiacetal. Okay? So either a 6 atom range or 5 atom range. Okay? And obviously you cannot start from that. The first carbon of the 1 atom you in the range is the carbonyl carbon. So this one of those oxygen in the alcohol, in the hydroxyl, it will be the nucleophile attack your carbonyl carbon. Okay? So 1, 2, 3. If you use this oxygen from this hydroxyl, you only produce a 3-member ring. Right? You want to produce a stable is a 6-member or 5-member. So 1, 2, 3, only 3. 1, 2, 3, 4, only 4. And 1, 2, 3, 4, 5. You want to use this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. You can also produce that. Let's see what you produce in this example is you can produce, sometimes you can produce both. So I think this example I'm going to show you is produce this 5-member ring. when you have a little bit of stereochemistry here, you have this OH on the top, and this OH at the bottom, and this part is also on the top. Now let's number the carbon 1 and 2, 3, 4, 5, and 6. For this chapter now, we are not going to study how we produce this kind of stereochemistry. From this one to get that one, give a difficult. But in chapter 23, we will see to change this kind of structures into the so-called Fischer projection. And this kind of structure we call the Haworth structure. So once you have the Fischer projection, and it will be very easy to convert from the Fischer into that. So we'll study that in chapter 23. So then, as I said, you can use this, the hemiacetal is useful because you will see those cyclic structures for those carbohydrate sugars. Right? And now the usefulness of the acetal is protection. Okay? So some of those alcohol is diol. As in this is the ethylene glycol. Ethylene glycol has 2 carbon and 2 hydroxyl. Okay? So therefore, this one alcohol is kind of 2 alcohol. And 2 alcohol can like produce acetal. Okay? Now what you will see this in this example, you will produce so we have the heptane now. So this H emitted from the aldehyde, and then we will have this acetal. Acetal, which means you have 2 OR. So your usual acetal, so this will be OR, and that will be OR prime. And it might come from 2 different alcohols, it come from the same alcohol. Right? Now here, both of the O come from the ethylene glycol. Okay? So this ethylene glycol have 2 carbon, and initially it's structured like that. And plus of water. So that is ethylene glycol has 2 carbon in it and have a diol. Now this is diol but has 3 carbon. Okay? You can similarly produce a protecting group on this ketone. I don't have a space on that. So if you understand, that's its structure. And we draw it here. That's better. Plus H2O. So once you adding on those acetal, you can take as like from those 1 molecular or 2 molecular alcohols, and then you can do take that off by using acid catalyst. Okay? I had one example. We have this acetal. It's just a generic acetal, and we were adding water with acid, and you can see this change back into the aldehyde and alcohol. Okay, now you can study the mechanism. Obviously, you can also study just predicting the products. Okay? The products of those acetals. And sometimes you might see those hemiacetals for those compound that has both aldehyde or ketone in it, and also the alcohol in the same molecule. Now this problem 17.11 is the first question. You have a cyclohexane now. So you just write out your structure first. Your cyclohexane now. And then you have the ethylene glycol. Ethylene glycol have 2 hydroxyl, 2 carbon, right? So if you put these two together, adding some acid, and you will produce acetal. Question B, you have a benzoylide. I saw on last exam, some people still don't know like what is the benzoylide, benzoic acid, toluene, aniline, right? So those easy questions, not too many points, like 4 points, but you don't have to really memorize what to write with words, just say like what is the name. Benzoylide has a structure like this. This is aldehyde. Aldehyde has a carbonyl and 1 H. So other ratings is 1,3-propane diol. H plus. This C here will still have this H. In addition to that, now this cyclic acetal has 3 carbon from the diol, 2 oxygen from the diol, then 1 carbon from the benzoylide. Both reactions will produce H2O. So this also produces H2O. So C, if you review the ratings give to you is this ketone. Okay. So this ketone reacting with ethylene glycol, acid catalyst, you will see you will produce also the cyclic acetal. Yeah, so plus, don't forget the plus H2O. D the same ketone as in C. But this time, the diol is different. So we have to figure out what is the structure. You have two metals in this diol, and these two metals will not get lost. I draw my arrow to the right, but also reaction is reversible. Okay? If you add acid, so that can break and go back to the aldehyde and or ketones and those diols. Okay? So these two C3, two metals went to there. Okay? Two metals and two metals. Next, we can use, because those reactions are reversible, we can use those acetal or ketones as a protecting groupers. Let's see, you want to produce, let's see, this one. Okay? Finish this reaction, and let's examine this reaction, what happens. Going from this alkyne with a ketone unit and into an alkyne with ketone unit, but with one more carbon. What do we do from Chapter-17? If you want to add one more carbon on the triple bond, we use what process? So if you don't have that ketone, if you start with this, let's say this alkyne, right? And this is H, you want to produce this, so this is one propyne. Unless you want to produce two butane, the CH3, C triple bond, C and CH3. You remember what you do to this to finish this process? Your first step. You take a strong base, NH2. In some of those agent solvents, that is A protate, maybe use ammonia. Right? So that you will take the H away, take the terminal H away. Then your second step is adding those methyl halide or primary halide. Right? Depending on how many carbons you want to add on. For this example, you can add simply adding the metal, the CH3 and Br. Right? So that will add the metal at the end. Now, why you cannot do this reaction straightforward to this reaction? This reaction not only have this terminal triple bond, also have this carbonyl. So when you use a strong base, I got an Na2 in the first step, and that also will reacting with this carbonyl over here. And your second step have that methyl bromide that can also reacting with your carbonyl. Or in the first step, as you do the reaction with this carbonyl unit, you produce this anion. Okay? So in this step, if I add in this, let's see, I change this into, so if I add in another C3 here, this become the carbonyl like what we look like in that one. Okay? Your first step, you will produce this CH3 and C double bond and C triple bond, and this negative ion. That's the result of your first step on the top. So this probably, for this one, probably not that bad because this cannot go back and take this easy because you are only produce a 3-member ring. But for this one, you have 1, 2, 3, 4, 5. So you can bending back, and you have enough carbon in the middle. You can bending back and attack the carbonyl carbon. The carbonyl carbon has a positive charge. So therefore, we have to protecting this carbonyl. And now you know how to protect the carbonyl. Okay. So the reaction will carry out like this. Now I will change that structure into the line structure. Okay. Because we have 6 carbon. Okay. And so you can draw your structure out like this. Now let's use our ethylene glycol, OH, and OH. So this will change the ketone into this acetal. Now, acetal is stable compared with the ketone. It's stable. You are not reacting with your those base, those strong base. And we are learning in Chapter 20. Okay? You can take your H away from this alpha carbon. Okay? And then that can reacting with your like methyl bromide. So then that will make it very complicated. Okay? Now this because you change this carbonyl into this acetal, your acetal have 2 oxygen on it. Okay? It's not the same as double bond oxygen. It's kind of you get some more electron from this 2 carbon and 2 CH2, so make that oxygen pull the electron from this carbon different weight, different length. Right? Or you use resonance. If you take a proton away from here, you produce a negative charge here, and then you try to use resonance. You cannot like push back and produce those Ylides onto those acetals. But anyhow, So we protected this this carbonyl. Okay. So next, you can use our usual procedures. See, let's see, we'll do the air conditioning, and first we'll take this. So this the acetal. This is the acetal. Now I will take our strong base, NH2. So who is this kind of review, right? Always in this orbital 2, you will see those some of the chapters you studied early, and now you will study again. So this will produce negative ion right here. And do nothing to this acetal here. If you use access those amine into, you probably can still pull some of those proton away from those alpha carbons. We have to look at those pKa, how much you can pull away. But for right now, if you just use one equivalent, so this Na2 is a strong base, it will react with those strong acid. A strong acid is that terminal H from the triple bond. So now this one, you can just add, for example, C3Br. Now you will have this C3 at the end. But we still have the protecting group only. Now to remove this protecting group, this acetal, and let's redraw it here. This time, I don't have to spell out the C3. If I leave the line like that means C3. So let's see, adding water and HCl. HCl is acid. And that will get rid of acetal and recover your ketone. Plus your ethylene glycol. And this is OH. Any questions or comments? So produce acetal is the characteristic reaction of aldehyde and ketones, not the reaction of carboxylic acid. If you take some of the acid and reaction with alcohol, right? And you will produce acetals. You will not produce those acetals. So therefore, we can selectively protecting the acid, the ketones or aldehydes. So that's the practice of this example, this problem. this molecule into alcohol. So this molecule have this ketone here, and have this acid here. Okay? So you don't want to do anything with this ketone. You want to leave this ketone, but you want to reduce this acid into a primary alcohol. Even though we did not study acid yet, the carboxylic acid is going to study in chapter 18, next chapter. Okay? But we studied alcohol. And then we studied how to prepare alcohol in chapter 15. We know like we can reduce the carboxylic acid with lithium aluminum hydride, which is a very strong reducing agent. If you use that directly on this molecule, you not only reduce this acid group right here, you also reduce that. But that is even easier to be reduced by the lithium aluminum hydride. So first of all, we have to protect in this part, then use lithium aluminum hydride. We will use this diode. The diode here did not react with your acid. Instead, it reacted with this ketone, produces this acid. Right? So now, where you like to argue, if you have an alcohol in a diode, don't need to like react with your acid, you use the Fischer esterification, produce your ester. Well, I think those are always competition. Depending on which reaction faster. So you put this molecule and add this ethylene glycol, and this reaction will go faster. So all those ethylene glycol will go on this, you don't have time to go on this produce ester. And you will learn to produce ester, the Fischer esterification is a very, very difficult process. You have adding acid with, if you just simply use acid with alcohol, you probably want to use anhydride or chloride, acyl chloride with alcohol, and the reaction will be much easier. Because otherwise you had adding like some acid, sulfuric acid and reflux for like 2 or 3 hours. Right, so therefore we protected this carbonyl. Right, so next, and you can reduce. So that don't have to rewrite or take that. What do we use to reduce acid into a primary alcohol? Not too much choice. Right? If for this class you will only see this LiAlH4. You have to use, if I, on the exam, if I wanted to specify this reduction process, I wanted to number 1 is use lithium aluminum hydride, number 2 is use water. Right? So then this will reduce your acid into alcohol. So alcohol is a benzylic alcohol, looks like that. You still have this over here. Right? What you're going to finally produce is that benzyl alcohol with the acetone on the left side. So the final step is to remove that acetone. So now let's put the lead right here. So what do you use? Just simply adding water and HCl or H2SO4. So that will get rid of your acetal and you will recover your ketone. Okay, so you will also produce your ethylene glycol. Next section is using those nitrogen-based nucleophile. Okay. So this time, you will take some of those primary amine or secondary amine. Let's first use the aldehyde or ketone with primary amine. With primary amine, you will produce imines. So imine has a carbon double bond to a nitrogen. The general reaction is you will go through the addition of primary amine onto the carbonyl carbon and produce a hemiamino. So instead of acetal, you have an amino. It's very interesting to compare you adding alcohol with you adding the amine. The difference is you adding amine as amine, primary amine like this. NH2 has one pair of electron. As compared with alcohol, alcohol has a structure like this. And you compare these two, adding on to, let's say, acetone. If you add alcohol on acetone, you produce acetal. Right? So let me say this one. So these two together use acid as a catalyst, you produce acetal like this. On the other hand, if you take ammonia, amine, or the primary amine, what we draw here, you produce imine. So why that's not always go like to produce something like also like acetal adding like two of those amines. So what these two together to produce is this carbon and N double bond and then R. if you want to see the similarity as the acetal, let me just see here, maybe I already use those, and then see what is the similarity of acetal with amines. And then we'll try to understand why that did not go all the way like that. If you want to take two of those primary amine with a ketone, very similarly, if you take two alcohol adding onto your ketone, you will have two of those single bond C to N, right? So you will produce something like this. N, H and R, N, H and R. This did not happen, so you can only actually, so this is not, you did not produce that. But here it is yes. So you can go all the way adding like two alcohol. You add only one primary amine, then that primary amine lost water and you have the double bond between N and C. So the difference is because oxygen is more electronegative. It's not that a good nucleophile, and it's also like not that easier to be polarized because N is a little bigger, O is a little smaller, and so therefore it will not stabilize your N will not stabilize your intermediate those carbonyl like hemiacetals, but your N can stabilize that better because you can donate more electron. It's a better electron donor. So you can only produce you produce a double bond between N and C. That's enough. It's very similar. You have two single bonds. Right, now let's see how can we predict the product. So usually we'll see you will produce the hemiaminol, and the hemiaminol dehydrate and give you the final the imine. For this first example, and you can think about you produce the let's see, I erase some of those there, so that's it. Probably I have enough space here. So this C, and we still have this H here, and it will produce this hemiaminol. Intermediate. Then this will see the mechanism. Okay. So then this will dehydrate, take the hydroxyl away. So that's the product of our first example. Lots of water, H2O. The second example is this cyclohexanone plus this isobutyramine. And it will give you this, they will give you this imine. The imine pretty much you replace the initial have a carbonyl double bond by a bond between the carbon and N. And you still have this isobutyl plus H2O. So all those reactions has like the common name for the nucleophilic addition. Now that's the mechanism. Okay? Then with the mechanism, so step one is amine acts as a nucleophile, adding to the carbonyl carbon and forming a CN bond. Okay? Let's take a simple example, simple primary amine. So we have this CH3 NH2. This is the primary amine. And we'll use benzaldehyde. I'm going to use abbreviation for the benzene ring. So I call the pH. Phenol. Okay. Carbon, double O, and H. So this is our benzaldehyde. Okay. 1 lone pair of electron on the N attack this carbonyl carbon and put electron onto the oxygen. pH, that is pH is for this group right here. Okay, so this is for pH. And this bond for this doesn't mean metal, that means let me just see this bond is already drawn like this, like this. That means it's bonding to somewhere else. Right? So that's, you understand, some people I use the C6H5, but you can also use simply CPH. That has a positive charge. Okay. Next step, the protonation and deprotonation, I'm going to run them together. Okay? So you will see this is pH. Carbon, and so now let's rotate this little bit. So we have this oxygen here, -1 charge, and then this H here, not going to do anything too much. And this N, now this is CH3, and H, and H, H and H. And this has this N right now has a positive charge. So we are going to deprotonate this N, one of this H, and we are going to protonate this up in the same time. You will take water to do the protonation, or maybe take acid, even though in the mean, and then you will take water to do the deprotonation. So use acid to do the protonation, then use water to do the deprotonation. sense? So this come from here, and come from here, and then this goes there, and this goes back there. So as a result, it's a kind of proton switch. And so you have the pH and the C and H are very loaded. I have this N, H, and C3. So the N don't have the cross charge anymore. Okay? So on the top, you see you plus H2O that come from the H3O at the lower place. So we will recover the H3O plus. Okay? So here this H2O become H3O plus, and there the H3O plus become H2O. So as a result, this become your amine. Don't have the positive charge anymore, and there you don't have negative charge anymore. So this is the hemiaminor. Okay? So you call this is the hemiaminor. Next step is the dehydration stage begins. Okay? We will take that H, C, H, and this is kind of alcohol, right? And you have this amine here, and this is CH3. Amine have the angle, have the long pair. So you first protonate to a protonation. That means you use some of the acid. And there's only one pair we land on here. And the oxygen is the plus charge. Protonation, that means adding an H plus. Again, you have a choice. You add in here or add in there. If you add in here, so this will break away, you will return back to your reactant. Right? So there are some steps will make the reactant going forward, even though they always going back and forth. So this time, we'll choose this protonate on this oxygen, and that's reacting going forward. Okay, so whenever you see something like the OH2 and N plus, that become a good leaving group. It can be like pushed out. Right? So this guy, whenever you see like in some of the process, this become a good leaving group that can leave like water. To make that that hemiacetal easier, usually you will use another lone pair, produce another bond. So this lone pair here will produce another bond. So let's rewrite here and O, only one pair of electrons that has positive charge. And we have N here, we have H here, C3 here, and lone pair here. So what happens is this lone pair come here, produce your double bond between N and C, which is double bond in the imine. Then this will push out this will break that bond between the C and O. So again, you're almost there. The last step, your N becomes positive charge. Right? So now you have this N and C is 3 and H. Almost like a imine. The imine will have the carbon nitrogen double bond. Now you have the carbon nitrogen double bond, but the problem is in imine your nitrogen is neutral, don't have a positive charge. So the last step is very simple. You take the water and you can deprotonate your conjugated acid of your imine. I should switch the place. I put the H there. It's difficult to take it away. Excuse me about that. So let me switch the location. Okay. So I will rewrite. I will write the method in there, and write. So this one is C3, and this is the H. So then I will room to take this H away. So now we have water here. Water attack this, and then this will bounce this electron back on nitrogen. And that's our final product. Okay, any questions? This is an imine. Any questions or comments? Okay, let's do the practice. Problem 17.14. Write the structure of the aminor or hemiaminor intermediate and the imine product formed in the reaction of each of the following. Okay? So you will write the hemiaminor. Hemiaminor has the carbon with the OH and with those amine on it. And then you will write your final product, the imine. Imine is the compound have a carbon and double bond. Okay? So the first one, you have the acetaldehyde and the benzylamine. So let's write them out. Acetaldehyde is this aldehyde. Benzylamine is this NH2, and then you have this benzyl. Right. So you are let's first write this our hemiaminor. Our hemiaminor it will have this this H here, and then your carbonyl becomes Z, and then you bond into your N and H. next, you do the dehydration. Okay? So you don't have to write the mechanism now. Just say loss of water. And you will produce the double bond between this and your N. Ready? So there's a long pair here. If you want to keep tracking our initial, we have a H here. So you will have a H here. This kind of compound, we call them imine. Okay, question. The next question, you will have this benzaldehyde and butyramine. Benzaldehyde or benzene. Butyramine H2N 4 carbon. So this butyramine. What is important to produce the imine? You make sure you have the sort of primary amine has 2H on the nitrogen. Okay? So whatever amine you use, make sure you have 2H on the nitrogen, then you can produce the imine. Okay? If you only have one H on the nitrogen, that means you have a secondary amine. And secondary amine reacting with those aldehyde ketone produces the enamine. Then your double bond is not between carbon and N, it's between the carbon and carbon from your aldehyde or ketone. So this will produce your hemiaminol. So your hemiaminol is N and H, and then you will have this OH and H. This hemiaminol dehydrate, that means minus H2O. This H, that OH loss. Produce a double bond. Again, this is imine. On the exam, on the quiz, relatively easy if you don't worry about the mechanism. You just take some of those carbonyl carbon and primary amine, you just replace your carbonyl CO double bond by CN double bond. Next example, you have this cyclohexanone. And I have the terbutyramine plus H2N. And this is our terbutyramine. And you first find out your hemiaminol. The hemiaminol, it will have this OH here. I have the N here and H here. Okay? And then this N bound into this terbutyl. Now this, let's see, dehydration, always just see minus H2O. It produces a structure like this. Even though this looks like a tertiary carbon, this amine here is still a primary amine. The amine's definition is a little different. Okay? Amine primary, secondary, depending on how many carbon attached on the end. Primary amine, that means only one carbon attached on the end. Okay? So the requirement to produce imine, you use aldehyde or ketone with a primary amine. Now, no matter what kind of alkyl you have here, the alkyl, tertiary, secondary, primary, doesn't matter. Yeah.
What about the ring?
The ring doesn't matter either. You can use this ring, that means you have a ketone, okay? And in a few examples, we also have aldehyde. Next example is you will use acetophenone, and you will switch. You will use acetophenone. Now you have the ring on the amine. Okay? So your reactant, acetophenone, is this. So you have an acetone, a methyl acetone. You call that is your methyl phenol acetone. Right? So you have methyl here, your phenol here, acetophenone. Now plus a primary amine that is required. You have H2N. The primary amine this time gone into a cyclohexanol. What it produces is first produce the hemiaminol. Then this hemiaminol dehydration, obviously minus H2O. double bond now between the N and C. Any questions? Yeah, there's a lot of examples. First, I think you memorize by the type. Okay? You produce what? You produce the acetal, or you produce the hemiacetal, you produce the hydrate. Hydrate, which means you're adding 2 OH on your carbon, or you adding H and CN on your carbon. Not too many new reactions. Some of the reactions reviewed. How you produce alcohol from aldehyde ketones? You use like the H2 plus platinum plus platinum, or you do adding the green out of organic lithium. So now we started this new section about produce enemies. Enemies is the product of aldehyde or ketone with secondary amine. Secondary amine, that means you have only one H on the N. Okay? So this general overall reaction tell you your amine has only one H on the N. Okay? And you produce this hemiacetal, very similar to hemiacetal we saw so far in the last problem. Hemiacetal, which means you have a carbon with N with hydroxyl. Now this time you do the dehydration, which means loss of water. You don't have an H on this N available to loss with the hydroxyl. So what happens? You are taking on those H from this product will come from your ketone or aldehyde, and you will produce a double bond between your carbon and the carbon like that. Now you compare, you think about if sometimes you have time, if you compare, if this is the alcohol, when we produce this acetal, you will have a OR here, and you have that part there. Then we saw what happened that is our hemiacetal. So the hemiacetal protonate this OH, the OH become water, gets lost. Right? Then we'll go on to adding another alcohol, then we'll produce the acetal. Now for adding those nitrogen nucleophiles, nitrogen is the better nucleophile. Right? So after you add, you have this long pair of electrons, and nitrogen is less electronegative. Right? So that means you will get less electron away from the carbon, so the carbon is relatively less positive. So you will not go through the adding or loss of water, adding another alcohol. So this carbon is kind of already stabilized with only one N. Okay? So if you want to stabilize this carbon here, you need to have a carbon double bond. You need 2 of those alcohol, which means you have 2 OR here, OR there. Right. So the reaction, let's first write what the product looks like, right? And then we'll go through the mechanism. Okay? Now here is a carbonyl. In this example, is a ketone. Okay? And here you have a secondary amine. Okay? So what you produce is this. So what you produce so those kind of guys this makes sense. Okay? This part comes from the double bond. And this is just our usual amine. Amine. Okay. So therefore, this name is a combination. Okay. So that means your amine have this N bound into a double bond. It's very similar as think about that enol. Right? Enol has a structure like this. Now you don't have an enol, you have an enamine, but I think some people call it enamine. Enamine. Now to get the mechanism, the first step, so we'll skip a few of the details, and we'll just write our, let's use this secondary amine as one example, NH, a long pair on length, plus one carbonyl. In this example, we'll use aldehyde. Okay, you will see how strongly this nitrogen can donate the electron compared with oxygen. Okay? Just with the help of this lone pair of electron on the nitrogen, it can donate enough electron onto your carbon-nitrogen bond and get rid of your OH. Well, OH is usually not a good diene group, okay? But in this example, I'm going to say this, get on that, and that, get on that. This ion looks like an amine, okay? Because it has a positive charge, it's not an imine, it's called an iminium. Right now, as we see in this iminium ion, right? So actually, we did not draw all those H, H here, here. Okay? We need an H to draw now. Okay? So I will add in the H because we are going to take this H away. There are many other H, show, right? Those are not in the chemical reaction. Okay? So we draw this H out. So this is plus the hydroxide is produced in the last step. Now that's adding the electron pair. So this is negative. Now you just use our usual electron arrow technique. So this come here, grab this H. And this electron move onto the bond between carbon and carbon. And this electron will bounce back into the nitrogen. Alright, so now you have a long pair of electrons on N. This long pair of electrons come from this pi bond. The H goes away, and then you will have a double bond between this carbon and this carbon. Okay? See here, you initially have a carbon, now you have a double bond. HOH is H2O. Okay, so this, a general name is an enemy. An enemy, which means you have a amine bound into a double bond. The En means double bond. Okay, I think we will finish this chapter and then we'll do the quiz, right? So there was the last section. The very, very powerful method of prepare double bond or alkenes for the Wittig reactions. So in the Wittig reaction, you use Ylides. Right? What is the Ylides? Ylides have it's kind of a molecular that have positive side and also negative side in the same molecule. The positive part, negative part. So the common Ylides is this kind of triphenyl phosphine, and then you have this carbon. Okay. So phenyl, this part, benzene as a substituent and abbreviated as pH. So 1, 2, 3, so therefore it's pH 3. It's a very, very active reagent. So that's written is probably the major common component, but obviously it can resonance. It can resonance. Resonance structure, you will have this pH 3, P double bond, and like that. Now in this resonance structure, this will be minor. So this one will be the major because Oxidation. So even though you have a negative charge on carbon, and you have a positive charge on phosphorus, but all the atoms there has oxidation. Phosphorus is in that group period 3, and you know from period 3 and below, you can use the d orbitals, so therefore you can have more than an oxidation. Right? So in this structure, for this phosphorus, you have 5 pair of electrons nearby. That is 10 electrons. So then you can use this Ylides react with aldehyde and ketone and produce alkane and double bond. And this type of approach is regio specific, as we know, like from those from that one reaction called the Diels order reaction. Right? If you take that conjugated diene and with some of those dienophile, because dienophile has a double bond. Double bond can be trans or cis. Right? So regio specific means if your initial double bond in the dienophile is trans, for example, then in your product you also have the trans on the ring. Okay? Similarly here. So you will specifically know where will you produce the double bond. If you want to produce double bond, you can do a retrosynthetic analysis, unless you want to produce a double bond like this. And now we know this Ylides, and adding on the carbonyl, which will be the aldehyde or ketone, and give you this specifically this kind of arrangement. Okay? So you know where the double bond, and then which side is on which side. Right? So for example, you want to produce this methylene cyclohexane, and this one. Okay? That means your double bond is here, not here. This kind of outside the ring, not in the ring. Okay? And one way to produce this, if you want to use this Ylides, the Wittig reaction, you will simply take your one of your ketones. In this example, you can take this ketone. And plus our Ylides, let's use pH for the phenol. We will have 3 of these. Then we have the phosphorus, and then the phosphorus bonding to the C, H, and H. And we want to use this resonance, even though this resonance is a minor contribution. Then this has a positive charge. Right? So that will give you specifically your double bond will be between this ring and then this S-ring group of C2. So now if you compare, if you start with this cyclohexane, right? And with there some other way to produce the double bond. Okay? You can do like the dehydration, okay? You can do the dehydrohalogenation. Let's see if you want to use the other way to compare this step here with this step. we'll use this space and here on the right. So we'll see this one become, let's use like that approach, think about do the dehydration or do the dehydrogenation, right? And obviously right now your carbon number is not right because here you have one carbon more than the cyclohexane. So therefore on that structure somehow we have adding a carbon. Right? So the other approach use here do the indication, use the Grignard addition followed by the dehydration. This Grignard, we know the Grignard can reaction with aldehyde and ketone also. Right? So now let's use Grignard. So basically we first will take the Grignard. You need only one more carbon. So therefore you can use C3MgBr. And your second step is doing some work up. Anybody remember these two steps will produce what kind of product? If you are adding C3MgBr. The C3 will attack what part of the molecule? And the C3 kind of have the negative charge now. Usually the carbon has a positive charge when the carbon bonding to oxygen or bonding to a halogen. Now the carbon is bonding to a magnesium is metal. Right? So this C3 is kind of a nucleophile, has relatively negative charge. Right? So negative charge obviously we're looking for the positive charge. Now this compound, which part has a positive charge on it? This is cyclohexane. What part has a relatively positive charge on it? The oxygen or the carbon in the carbonyl? The carbonyl carbon. Okay? So therefore your C3 will add on. Remember this? The quiz we did like yesterday. Yesterday we took some of those Grignard and we initially produce the O1 negative, right? So then O1 negative ever subtract H, and then you have this OH. Right? Now this approach just as a compare. Right? We know we can precisely specifically adding the double bond on this side by use the Ylides. By use the Ylides. But if you think about the other process, if on the test, you are asking you to produce this methylene cyclohexane, and you use this approach, you will lose some point because you will get a mixture of these two possible products. Because if you take this the next step and you add H2SO4, like adding H, right? Now you see, like you review like from that chapter of alcohol. Whenever you have alcohol and you add some of those acids, you hate. But even this reaction, even you study in the chapter of alkene, double bond, in orbital 1. Right? So what happens if you have alcohol and you add acid and you add heat? Alcohol with acid and heat, it will go through water reaction. It will undergo water reaction. Yes, sir? Do you have some idea? What reaction that can do if you have alcohol with acid and with heat? Andy, what reaction it will do? If you have alcohol and you add acid and then you heat. Yes, what is his name? dehydration. Okay. So here, tertiary alcohol, right? And dehydration. Dehydration means loss of water. You can produce a double bond. Right? Now the problem is where you are going to produce the double bond. You're going to produce the double bond in the ring or on these two carbons. Right? So it's all possible. And you probably get a little more for the one. Let's see which one will be more, depending on which is more stable.